Okay, good morning everyone. Welcome back. We're very happy to have Sean telling us about quantum field theory from matrices.
Thanks, Bill. It's a pleasure to be back in Durham after a long time, in fact. So I want to describe a path to quantum field theory, so hopefully appropriate for the meeting. That is not that you either start with quantum field theory or a lattice, right? And space is presumably emergent in some sense, and it's certainly emergent in ADS-CFT type examples. But in ADS-CFT, the continuum space is not built from a lattice; it's built from a different structure, and so I think it's clearly urgent that we understand really how a locality and a spatial continuum can arise from matrices, which is what happens in ADS-CFT. May not happen in our world, but it's a different path to quantum field theory. And so in this talk in particular, I'm going to talk about a very simple example. So my global strategy is space definitely can come from matrices. We don't really know how, except in one dimension where it's a bit too simple. So let's start with the simplest possible models we can. And so the example I'm going to talk about today is what's called a fuzzy sphere. And so I want to describe how to go from matrices to quantum field theory on a sphere. So the quantum field theory is going to be on S2 cross time. That's going to be where we're heading. The time is, we start with the time, but we don't start with the sphere. So the fuzzy sphere is actually a venerable object in string theory. It's been around for a long time, and so, but I want to bring a sort of entanglement perspective on it. Okay, so what do I mean by matrices? So the example, I'm going to work with a pretty concrete example, actually which we studied quite a lot in this paper with my student Shisha. And so here's a Hamiltonian. So the Hamiltonian is trace. I'll tell you what that trace is in a minute. I'll tell you what everything is in a minute. Sum over I squared. I'll define everything in a minute, and V of x. I'll tell you what V of x is too. Okay, so that's going to be 3, x1, x2, x3. We might also call them x, y, and z at some points. Are n by n emission matrices. This is just classical at this point. Okay, this has nothing to do with the Hilbert space, right? The classical degrees of freedom are n by n matrices, right? So life gets a bit confusing because there are going to be two senses in which things don't commute. Things won't commute quantum mechanically, and they also don't commute under the matrix multiplication. All right. So far, just matrices and no quantum mechanics. Okay, and so pi I are the conjugate momenta to these x's, and v is a potential. We'll pick certain potential in a minute, but this is the general form. Okay. This is purely bosonic. Also, you could have principal have fermions. So. These kind of model back to this trace is over the matrix trace, right? Not a Hilbert space trace, just a Hamiltonian. Okay, so this has a UN gauge symmetry. It's a UN gauge symmetry is imposed. It seems to be loads of space over here. And so the generators are matrices G. Okay, I'll put the 2y here, but it'll make a drop very soon. Sum over I. Xi pi I. Okay. So again, this is a matrix, right? This has A, B. This has n by n indices. Right? Nothing quantum. It's just the classical generators of S2n at UN symmetry. Right? So it's X and pi. I mean, this is just. Okay, nothing fancy. Right? But think about it as a Hamiltonian point of view. So these are the generators that commute to the Hamiltonian. Yeah.
Can I ask, maybe it's premature, but why 3 of these? Why not general?
It could be any number because they're going to give me this sphere. So this, I'm going to write down a nice model, but so good. No, that's a good question. So if there's one matrix, things are very easy. Yeah. So maybe indeed because there's a broad audience, let me contextualize. So theories in this class, they sit between two extremes. Okay. So the easiest matrix on mechanics is just of one matrix, right? So you have H equals trace pi squared plus V of x, so there's only one matrix. This is completely solvable and integrable and actually has a lot of rich physics, but it's you diagonalize the matrix, because there's only one matrix, and you've gauged the UN, you can just diagonalize the matrix, and it becomes a many-body problem for the eigenvalues of the matrix become like particles, and then our many-body friends can have fun solving it. Okay, so this reduces to a many-body problem, turns out to be integrable, closely connected to Calogero models, etc. Okay. There's still fun things in the so-called non-single sector of this model, but this one's basically solvable. At the other extreme, the hardest I don't know, but maybe the most symmetric, or the hardest or the most interesting would be this BFSS model.
Actually, can you define what you mean? What is Hilbert space?
So this model. So this model is let's do the classical model first. So it's a classical model of one n by n matrix.
Yeah. So what does it mean?
And it has this gauge symmetry. Okay, it's like very good. Okay, yeah, good. So so suppose you have. Sorry, this goes too much back. But let's start really at the beginning. Suppose you have a harmonic oscillator, right? And the Hamiltonian is p squared plus x squared. Okay. Let's have two harmonic oscillators, q squared plus y squared. Okay. Let's have n squared harmonic oscillators. AB. Okay. We can also write this as trace p squared plus, if they're symmetric, let's say trace p squared plus x squared. Okay.
I think this answers.
Well, one second. This would be the simplest matrix, the very simplest matrix. Quantum mechanics is just n squared decoupled harmonic oscillators, for example.
Okay. But then why did you say Calogero?
Right. Good. So this. Right. So actually, it comes out of this model, in fact. So another way. Right. Say you want to impose this UN, this sigma, this UN gauge symmetry. Okay. So that makes it a little bit non-trivial.
So that's not the same as this one.
Not quite. But now we can gauge it. Let's gauge this. Yes, exactly. So now, now let's gauge this symmetry. Then at a classical level. Actually, you can diagonalize the matrices. Okay, sorry. Let me say this right. Yeah, that's right. And when you do that as a measure factor, and that becomes a repulsion. There's this van der Waals determinant. I don't know. It's okay. Let me. What's the very simplest? Okay, so I think the very simplest way to do it is
just that the Hilbert space is not n squared harmonic oscillator.
Not when you impose this gauge constraints. Yes.
Okay.
Yeah. The same sector under the gauge constraint. Then it's just the eigenvalues of the. Okay, let me show. But it is quite simple. So let's quantize this guy. So naively, if you just quantize it, it would be d squared dxab squared plus xab squared. Okay, that would be the naive version of this. So now let's diagonalize it. You just do x is u, x diagonal. U diagonal. That's just a change of variables. It's like going to polar coordinates. This Laplacian becomes, well, there's a measure term which may not be 100% correct, but it's something like this. Practice, and then there's an angular bit, and then this is just like the same. And so this thing is producted over A and B. So product over A. This is called the van der Waals determinant. So the measure factor. If you absorb this into the wave function, so if you write this out, okay, so this is 0 on the singlet sector, which is annihilated by the angular terms. If you expand this out, you get something like, and there's in general there's whatever potential you want, and then there's another term which ends up being this. So that's your color draw. So it comes from the measure factor when you rotate to the eigenvalues. Yeah.
But basically, because of the gauge, you actually it's and harmonic oscillator.
That's correct. Yes, with only one. That's right. Yes. Yes. I mean, people. You can also start studying the non-singlet sector, and that is also interesting. But yes, that's right. The simplest sector is just yes.
Suppose the projection of the singlet sector is tricky to do with that.
It's tricky, or is
Gauging is just projecting into the singlet sector, right? And suppose that projection is tricky.
I mean, it just reduces the degree of what it's not tricky. I mean, it's doable.
Well, so how is that thought that you started with some quadratic theory radio?
Well, it's a gauge constraint, so not all the states count, right? But by the way, this is also actually, I mean, sorry. For example, suppose we didn't have x squared here, but the general v of x. Okay, so this you could still do this. So this now would not be a solvable quantum mechanical problem, but this is still a very useful thing to do. And so actually, at large n, actually in general, you can solve all of these. These are now anharmonic oscillators, if you like, with a bunch of couplings. But because the couplings have this UN symmetry, you can diagonalize and go to some integral type description that you can solve. Yeah.
I think what you said here is there are two different commutators at play, right? There's the n by n matrix commutator and there's the quantum.
Yeah, well, so far here I thought it was classical. I just went a bit quantum here just to get to this. That's the quickest way to get this measure factor in. That was so I was preempted. And by the way, these don't write down in these formulae that probably things wrong with them, but spiritually they're correct. So actually, sorry. Yeah, exactly. So if you expand out this, you get this kind of term. But if you absorb it into the wave function, so you let psi be this random one determinant times psi tilde. No, I think this might be back. Maybe it's okay. If you do it properly, it just eats out the measure, like the same way when you're doing some basically symmetric problems in quantum mechanics. If you put an R in front of the wave function, it simplifies things. Okay. If you put this measure factor drops out, and this guy just obeys n decoupled. So this wave function ends up obeying. Okay, so you can actually get rid of this measure factor by multiplying it in the wave function, and then for any potential, so here you had n squared coupled oscillators, but by diagonalizing it, you get n decoupled quantum mechanical particles moving in this potential. And they're fermions, because actually there's no mods here. So permutations are included in the UN symmetry. So this wave function has to be invariant under permutations. This is odd, and so this has to be odd as well. And so what this problem, this original n squared bosons, the singlet sector of that is equal to n non-interacting fermions. Okay, and moving in a potential. And that, so then you get a Fermi C, and the Lorentz excitations and ripples of the Fermi C, and actually, okay, I mean, it connects the bridge with what I'm saying, because this is the simplest example of an emergent space, right? These fermions, you can bosonize them, and then the Lorentz excitations are the density of fermions moving in this potential, the collective motion of these particles. And so this guy, this matrix quantum mechanics can be mapped onto a 1 plus 1 boson. Okay, this is 0 plus 1 matrices, 1 plus 1 boson, where the plus 1 is actually the Fermi C that's built from these eigenvalues. Okay. So, but this is too simple. Okay, so this doesn't count. So this was understood in the 90s, and
I don't
yeah.
understand what is emerging here.
Good. So there's no locality. This has locality in time. So there's a second order time derivative, but there is no space. It's just a bunch of coupled oscillators. If you these fermions, well, this now is local.
Why are they fermions?
They're fermions because the original wave function has to be annihilated under UN. UN includes permutations. When you diagonalize, there's still a UN. There's still something left that permutes these eigenvalues. This has to be invariant. The measure factor is odd, so this thing has to be odd as well, and so they're fermions. And then they build up this fermion. So now you have n of them. So you have n fermions in potential. They build up a Fermi C. And then you can actually exactly build them, but more physically, the Lorentz excitations are the ripples of this Fermi surface. And these obey a wave equation that's local. So you really get d squared dt squared of some negative density of eigenvalues minus d and dx squared equals 0. So this now has 1 plus 1. It's local in the plus 1 that did not exist here. So this is a 0 plus 1 model that we map to a 1 plus 1.
But your V of x is setting some finite size.
Yeah, yes, that's correct. Yeah. Yeah, it can be V of x doesn't matter. So
But it traps your fermions into one location in one direction.
well, they bounce back and forth. There are a lot of these fermions. So if all the ends are in the right place, this is it's a somewhat big space. I mean, this X is meaningful. It's not just there's just one mode, right? There's like a W. These are very highly excited states, so there's a lot of motion. You can build a wave packets and the particle can bounce back and
Yeah,
forth.
but it's still like in a harmonic trap.
Yes, but actually, so
You can choose a potential
yes,
however you want.
right. And just there's like a tangent over tangent, but just so should you ever look this up, what people are particularly fond of actually is an upside down this case with the infinite C on one side, and there's this double scaling in it because the density of states diverges as you go towards the tip of the potential, and so then you can really get a lot of modes living there. And so the really correct continuum limit is you have to tune this thing to the top of potential, but it's too far removed. But the thing is, with one matrix, it's really basically solvable, and you do get a space from the eigenvalues of the case. But all the interesting cases of ADS-CFT involve more than one matrix, and that's probably quite important. And when you have more than one matrix, you cannot diagonalize them all at once, and you need to deal with more stuff. And so that's what we do not have a lot of tools for. Okay.
So, I mean, what about Lorentz in
Yeah, it's really non-trivial. Yeah,
Okay.
it's.
What about if you have fermions and bosons? Do actually the inertia with the same speed?
Yeah. Well, this model is really interesting. Yeah, I think there are supersymmetric versions of this. Actually, I don't know. Yeah, pass. Yeah, actually, so I think. Yeah, not sure actually. Yeah, not sure. Well, I mean, there's a wave equation that has a speed of light. I mean, in that sense, this Lorentz invariant. I mean,
For any potential.
yeah. But this is true for any potential. Yeah.
What about nonlinearities?
Yeah. So because this thing is integrable, it basically is exact. But right, there are nonlinearities. Yeah, actually, that's a good point, which I think may not be Lorentz invariant. You're probably right that they're not Lorentz invariants.
So the speed of light is set by the function velocity?
Yes. Let me move on because this is I'm not a super big expert on this, but it is helpful that. All right. So, but we need definitely more than one matrix is necessary. So, for example, roughly a very heuristic picture. If you imagine having two matrices, you can sort of diagonalize one of them, let's say, then you can't diagonalize the other one. And so they're the off-diagonal modes that are you can associate to pairs of eigenvalues, right? If you give an off-diagonal mode has two labels, and these are like particles. The off-diagonal modes are very heuristically a bit like strings that are connecting the particles. Okay, and so more than one matrix starts to connect to richer microscopic things that we like. And certainly when you have black holes, then you have n squared degrees of freedom, so eigenvalues are not enough. You need the whole matrix. So probably to get another way to say that is that in string theory, this is sort of a there are stringy corrections. This is not really a substringy locality, and to get a deeper locality, you probably need this extra structure. All right, so I'm going to take the case of this potential is going to have a particular form. So now we're back to three matrices. Oh, I didn't finish what I was saying here. I'm sorry. So the easiest one is this one with one matrix that is basically solvable, and the biggest and most beautiful one is this BFSS theory. That is maximally supersymmetric. And it has nine matrices plus a whole bunch of fermions. Okay, so many matrices plus fermions. Right, so BFSS is the dimensional reduction of n equals 4 superangles, 0 plus 1 dimensions. Okay, so it's like a big maximally supersymmetric thing. So this is very hard. This is very easy, and we're trying to make a living in the middle. Okay. I want to be so that the vision is going to be a little tortoise. Slowly walking up. Yes, sir.
And you also find ways to symmetry.
Yeah. So let me say something about that in 1 second. So this model has this potential. I should say in this paper, we looked at a particular model with two matrices that has some quantum Hall-like aspects to it. Actually, David Tom is a really well expert on. But this model, I think, is also a bit too simple. There's not really a dynamic. All the models, the boundary modes, and the boundary mode is really just described by one matrix. So I think this what I'm about right now may be the simplest model that has some Hall dynamics more than one matrix. So SJ. So it's all classical still, okay? So all these commutators are just classical. So here's the potential. If you expand that out into 3 terms, right? It's a square. This is for people to connect it. Then you get a sort of commutator squared term, which is a typical thing. You get a mass term, and then you get an epsilon times 3x's, which is sort of a coupling to some free-form background to get strengths. So this is a particular potential, but it's just total square, okay? And this is supersymmetrizable. So this is actually the bosonic sector of what Tarak and Nuss called mini BFSS. Actually, it's more like mini BMN, unfortunately. If the MX is like BFSS. So the X's are still Hermitian. So okay, BMN. It's another very. There's two. Something called BFSS and something called BMN. So this is a model. So you can add fermions that will make it supersymmetric, and for that it's actually pretty important that this thing is the exact square. And we actually looked at this paper. We actually did some numerics, some machine learning, even numerics on this model. But that's not what I'm talking about today. Today I'm just going to be talking about the bosonic sector, which is this. But it is supersymmetric. Someone asked about fermions. It is supersymmetrizable. Now, there's one parameter in this potential, which is this nu of v. Sure. And what's nice about this model is that when I think it's the nu goes to infinity limit is semi-classical. Okay. meaning that basically the potential term just becomes very big, okay, and so the leading effect is the potential wins. You can rescale things such that you use out the front of the potential if you want. And so this, now semi-classical, and literally the matrices themselves are semi-classical. Okay, so this is where we're gonna start. Okay, so let's start with the classical ground state. So the classical ground state of this, right, is when pi is 0 and you sit at the minimum of the potential. Okay? So the classical ground state, and this is a total square, right? So the ground state, you just have to set the thing inside the square to 0. So the classical ground state is xi, commutator xj. So yeah, everything is just big classical matrices. Is I mu epsilon I jk xk, which we will recognize as some dearly beloved commutation relations of SU2. So the solutions to this are representations of SU2. Okay. So actually, especially in these supersymmetric theories, you can actually choose any representation and they're all degenerate. But for our purposes, we're just going to take the sort of most irreducible one. So the fuzzy sphere, this is the definition. The fuzzy sphere is the n-dimensional, this is xi classical, is nu, right? We have to scale out this factor of nu. Times ji, where these are the n-dimensional. Remember, these are n by n matrices, right? These are not Pauli matrices, right? There's a U2, SU2 commutation relation, but they're n by n matrices, right? So we take the n-dimensional UM of U2. I'll write out very explicitly for you in a second.
Is this only some Newton pinky limit?
Sure.
This commutation relation is exact. The commutation relation is exact. Is it some?
Yeah, this is the minimum. This is the minimum of the classical potential.
Okay.
Well, it's just the minimum. This potential is an exact square. So classically, right, it's the potential and the particles are sitting at the minimum. So the minimum.
It is a saddle, right? You just take your coordinates to be constant.
Well, it's a minimum, but constant. So classically, what's the type of potential? The particle solution is pi equals 0, x equals x min, right?
That's right.
That's what a particle. So that's the classical ground state.
Classically, like you said, any representation works.
Yes, there is yes. So this, right. So yeah, that's the scale. So I'm going to consider this one. And in fact, in the supersymmetric, sorry.
And then you can work around.
Actually, you know what? I'm sorry.
You
Yes,
fix
I'm
it,
gonna.
right? You fix and
No. Actually, I'm sorry. No, wait. Actually, I got to get confused about something because I'm going to consider perturbations, and the only zero modes are going to be pure gauge modes. So actually, I think this may be. Let me take my mind a second. We're definitely going to consider this, and I'm going to consider fluctuations around it.
The fluctuations are fine, but there's a sum of partitions, ends.
Oh yeah, there's just other minima. Yeah, there's not a modular space. Yeah, right. There is. So indeed, this is not the unique minimum potential, but it is a common minimum. So semi-classically, let's just work with that.
In some sense, it's unique because of the gauge. I mean, at least within this family, it's unique because of the gauge symmetry or not.
No, I don't know. But
Sorry, is it really true that mu scales out? Doesn't it have to be the mu that Casimir representation?
No. So nu does scale out. This is the ground, the classical ground state just has to obey that equation, and clearly x just goes like this and it drops out. And U is not Casimir.
But I mean, of course,
Casimir
you
is
can do arbitrary rotations of these matrices, and that's also.
UN, yes, of course,
That's
yes.
gauge symmetry.
Absolutely,
so,
that's
okay.
correct. There's a UN orbit. Oh, that's correct. Yes, sorry.
Okay.
Wonderful. That's correct. These, yeah, if I do that, these are all ground states. Yes.
But because it,
Yeah,
you
well, let's just
consider
fix
that as a gauge, then that's
That's
really-
correct. Yeah, we'll just fix one. Indeed, that's correct.
So what's the justification for just choosing one minimum, right? Not all the others, or it's
So
just
in-
simplicity of presentation?
So, in what I want to do is, the objective today is to understand how quantum field theory comes out, and I want to build a space, and if there are other solutions, like, it doesn't matter too much. I mean, for this purpose, I just want to get a state that represents an emergent space, and if it's metastable, I'm not caring too much.
I see, okay, so all of these minima potentially could emerge other spaces?
Yes, yes.
But you could probably penalize members somehow.
So,
You could probably penalize among these.
Finally.
Yeah,
Yes, I think it's that's right. And I actually think that in the bosonic, let me not. It's actually a bit subtle. So actually in the bosonic theory, we did actually Shisha did numerics on the supersymmetric and so the bosonic theory, the actual minimum is x equals 0 basically. In the matrices just want to all collapse to 0. In the supersymmetric theory, I think that this is the minimum, is the actual minimum. But so it does matter.
It's all the Woodson index with some of the partitions there.
So let me
Let's Sean continue.
let me just this may be a metastable minimum in the quantum theory. Okay, it is. I will look at fluctuations. The fluctuations will be positive, but there could definitely be other minima. In fact, there are other minima. I'm not going to worry about that. So symmetrizing is probably a good idea if you want to start stabilizing these things. Very good. Where was I? Good. Okay. So this is a classical minimum of this, and so let me just write it down very explicitly. So and indeed up to UN rotations, you can pick a representation that looks it's going to be quite useful to have it very explicitly, and then let me write down J minus also. So J, we're going to diagonalize. I'm going to diagonalize J3, and so this basically is a bunch of integers that goes from L to minus L, where n is 2L plus 1. Okay, so it goes from plus n over 2 to minus n over 2, so on the diagonal. J minus, which is like J1 plus minus I J2, is lower diagonal, so it has zeros here. And then it has the square root of n minus 1. So the typical term looks like little n minus little n, square root, all the way down to, back to n minus 1. And then j plus. Okay, so this is what you'd expect, right? They're raising lower operators off diagonal, but there's a particular form that will become important later. All right. So now, let me tell you something that we did in this paper. Although I think this general rule would appear otherwise. So given this, let's expand about this minima. And so let's write xi is xi classical plus ai. And in fact, actually, AI doesn't have to be small. What I'm about to do is going to be exact in AI. So remember, this is just this new AI. So if we expand this potential, if we plug that into here, they're going to be different terms, right? It's going to be, well, the leading term will vanish, right? Because we're minimizing the potential. Then there'll be linear terms which have an x classical with an a, right? Here. And then there'll be a with itself, quadratic terms inside. So it turns out that v of x is just equal to, I'm not dropping anything, mu squared over 4 trace Fij squared, where Fij is Ji Aj Jj I plus I of mu I Aj plus epsilon ijk ak. Whatever. So these are right. It's 0th plus first order. So there's a 0 plus first order term, and this is all the second order terms. It's exact. I haven't dropped anything. So
Sorry, is it the same? Why do you have a first order?
this one.
Yeah.
Yeah.
It drops because it's the same. It's a
This whole thing is the potential is this whole thing squared. So it is actually second order. And this is actually fourth. This is actually fourth order.
Okay, sorry, yeah.
Okay, so this, this is going to become f mu squared very, very soon.
Is there some fancy way to understand how that happened from like, I don't know, SU2 algebra or something? This looks very nice, or is it?
I'm not sure. What? No idea what time it is.
38 minutes in.
Oh, okay, good.
Sorry, sure.
There's no talk this afternoon, right? Sure. Yeah.
So it's the same under this, with the definition, sorry, this is my customer AI, potentially you have before terms of this year. Say that under this field of definition, potentially you have before terms of this.
Right, so this term, that's all. Okay, so, and pi, right, so there is pi classical is 0, right, and so pi is just pi, like a conjugate. Very good, so now I'm going to show you how, these are actually all, I did not invent any of what I'm about to tell you. I'm going to show you how this, so the Hamiltonian now, right, is trace of this squared plus this. This can be mapped onto, these matrices can be mapped onto functions on a sphere, right? This is called the Moyal map. So we're going to do another one, this thing called the Moyal map. So we're going to, the maps, matrices, these matrices to functions on the sphere. So this is how it goes. So first you build matrix spherical harmonics. So first you build certain special matrices, I call them y hat, lm, jm. They're called matrix spherical harmonics. And they, so m goes between j and minus j as usual, but j is capped at n minus 1. Okay, so they're in one-to-one correspondence with spherical harmonics, except there's a cutoff on the angular momentum. And this has to do with the finite size of the matrices. So there exist these matrices, and what are their properties? Well, they obey Ji, Y, Jm. So these are commutators, just everything's classical. Is J plus 1, Y hat Jm. And they also obey J3, Y hat Jm is M. And this is intimating already that this is the way non-commutative geometry works, is that commutators become derivatives, right? So if this is like the Laplacian equals jj plus 1, it's like L squared, right? And this is like L3 being m, right? So you can construct these matrices in basically the same way that you normally construct spherical harmonics. You use these you use these raising and lowering operators. You find the matrix is annihilated by j minus to the n, and then you act with j plus, and you build up all the other ones. Okay, so these are built. So these y's are you build them algebraically. So algebraic construction. Completely mirrors the normal construction of spherical harmonics. Okay, so just believe me that they exist. Yes.
Another way to think about notation. So YJM is an n by n matrix.
These are n by n. Yes.
So the index are separate triple commutators made on the outside. JI and JI.
Say again?
Index JM. The indices of the triple
This goes like this. Yeah, the numbers should work.
For each J and M, it's a matrix.
for each chain.
Yes, sorry, these are not the matrix indices. Yes, well, sorry, indeed. This is all sub AB. That's right. Yeah, yes, thank you. Is that clear? These are J and M are not the indices of the matrix. They are labeling the matrices. Right. They're n by n. Sorry. Say again? Yeah, n is the size of these matrices. L is not J. That's why I correct the best, yes. So I don't need to introduce L. I could call this goes from basically n over 2 to minus 2 essentially.
If you have to map to the sphere, could you just work on R2?
On R2. Yes, so well, okay, very good. So the fact that we're expanding about this computation relation is only because it's here. But there are other, for example, there's if you had something like if the classical matrices had, let's say there were two matrices and they obeyed this, this would be a non-permuted plane. Right? So the computation relations in the background determines what kind of space you get. And so we're doing a sphere is a very nice one. Yeah, that's so actually this model, this paper. There's a non-permuted disk, so you can have different spaces. Yeah, exactly. That's right. So that good. I'll emphasize that again in a second. That's right. Okay. So now what you do is you expand these A's, the matrices, in terms of these matrices. Right. So we can write our A as a sum of some coefficients. Times these matrices. So now this has an AB index. This has an AB index, right? This is just a bunch of indices, but this is not a matrix anymore, these are coefficients. Now, I'll tell you the details in a second, but basically what happens is that if you take this and you plug it in to the Hamiltonian, right? So the Hamiltonian is trace now pi a squared plus b squared over 2 f by j squared. You plug that in. You do the trace, right? The trace over the matrices. You're going to get a bunch of, you're going to get the Hamiltonian in terms of these coefficients. That'll be the same as some normal functions integrated over a sphere, where you replace these with spherical harmonics on the sphere, right? I'll write that down. Okay. So you plug. So we plug in this into H. Do the trace of the matrix trace, right?
Probably like what orthogonal and Frobenius nor scale order.
Yeah. Oh, sorry. So maybe I'm not sure. So indeed, sorry, I should have said these guys are orthonormal as well, right?
Okay. And the Frobenius scale order.
Is that this?
Yes.
Is that
Do you also want to expand the phi of A in terms of the matrix harmonic.
Yes, also, yes, that's correct. Yes, thank you. So, indeed, so what happens, so you can imagine what the Moyal map is, it tells you this is how it's going to work. That if you plug this in, you do the trace, you kill all these guys, you have some function the A's, and then you integrate back in a sphere, and you rebuild, so we're going to rebuild a function AI of theta and phi, which is the same coefficients, but now with the usual spherical harmonics. Yeah. Okay. So given a matrix, like the most basic thing, given a matrix, I can expand in these spherical harmonics. I take the coefficients, I put the normal spherical harmonics back in, and I get a function. Okay, so it's a map, a very explicit map between matrices and functions.
But that only works if n goes to infinity. Right?
No, we'll get there. So these functions, you can certainly do this, but this is not all functions, because indeed, as you just said, there's a cutoff. So it's all functions angular momentum less than. Yeah. So how does so if you do this, so the Moyal map, the content is that traces turn into integrals over the sphere. Okay. Commutators with the background J's turn into derivatives, where Li is sort of a derivative on a sphere. And multiplication of matrices maps onto this so-called star product of the corresponding functions. And I'll tell you what this star product is in a second. Well, so the star product just means that I take the multiplication f, it's stupid, I take f and g, and multiply it by, and then I use this norm to extract the Jm component of it. The obvious thing, right? So you multiply two. Each matrix maps to a function. If you multiply two matrices, you get another function. And but this product, that's not the normal multiplication because of this cutoff, right? If you multiply two functions with a cutoff, if you did normal multiplication, you would generate higher harmonics, right? And this multiplication shows that you don't do that. So it's a horrible non-local thing. Yeah, that's right. So yeah, exactly. Okay, I'm gonna write this. Right. So indeed. So as n goes to infinity, the star product becomes the normal product, and this is actually a property. So these matrices, spherical harmonics, have some algebra, and these coefficients, this bit, goes to 0. So what this actually is going to map you onto, so this function, this Hamiltonian maps onto a non-commutative field theory, meaning there's like a field theory, but all the products of these horrible star things, but in the n goes to infinity limits, it becomes a normal field.
Just for the logic, the found standpoint shows gauging when you start with fluctuations, right? Yes. The fluctuations stand for so they're commutators of x and unitary.
I'll tell. Yeah, that's fine.
So this is not going to correct x.
No. Sorry, this is fine. So give me 2 minutes. I promise. So what? Okay, to answer you now. So this is going to become a Maxwell theory on the sphere. The gauge transformations become gauge transformations of the Maxwell. So I mean, it's all fine. They're still there. They go along the ride.
So Sean, I feel like people always said non-commutative field theories somehow aren't Lorentz invariant and so on, but it sounds like your regulator is actually totally.
Well, bad things happen, and it's going to come back. But let's leave that till. So if people who are unlucky enough to be alive in the sentience in the early 2000s will remember there was a lot of discussion about non-commutative field theories, and they have some unpleasant UVIR mixing properties. Okay, but if you take the strict n goes to infinity limit before doing anything else, And we're going to come back, but that's going to be an important point.
But it is SU2 invariant on the sphere, is that right? Every step of this stuff.
Yeah, that's right. Exactly. Yeah, I'll say that. Yeah, exactly. So what this is all some very extended background. So I'm just trying to show you. This is the path to quantum field theory bits. I mean, mainly I want to talk about some calculations with the matrices, but I think it's useful. This is some intuition that is not so widely known nowadays about why matrices are connected to space. That's all. Okay. So when the dust settles, yeah, maybe I should. Yeah, well, so so we had this Hamiltonian, we expanded the spherical harmonics, we did the trace, and then we wrote it as an integral over a sphere. Okay, these are all exact steps. We get that the Hamiltonian is nu, the integral over a sphere, half pi I squared plus Fij squared. Right, so this Fij is literally this Fij. Okay. But now, where Fij, remember the commutators become derivatives, right? So these commutators, the j's, become derivatives. Right? And this is the whole. And the basic point in non-graded geometry is that the commutators obey the Leibniz rule, derivatives obey the Leibniz rule, so commutators are derivatives. Okay, that's the in a nutshell what it's all. So okay. No, minus. So these are now these derivatives on a sphere. And let me take the n goes to infinity limit by this time. Yeah. Let me take new large. Forget about that term. Okay. So right, and I can regroup these. Okay. So this have three. This is not quite a gauge field on a sphere because it has three indices, right? And the sphere only has 2 dimensions. And so this decomposes into a gauge field on the sphere and the scalar field that is like the transverse fluctuations of the sphere. Okay, so you can define phi as n dot a, where n is just a normal vector to the sphere, and b, which is n cos a. Those are the components of a along the sphere, right? So n.
What happened with quadratic then?
I think it ends up being 0. But, you mean that one?
But phi doesn't have kind of.
Sorry?
Phi doesn't have kind of.
It does. So this pi, there are three terms here, and so if you do this decomposition, and you can define f to be n dot curl b. So that's like the f. So the f on the sheet. Then when everything's finally settled, you get this Hamiltonian, nu omega, half the kinetic term for this b, the kinetic term for phi, half f minus phi squared, so half phi squared. So this is a U1 Maxwell on S2 coupled to the scalar fields. And the scalar field is literally the fluctuation, like the geometric fluctuations of the sphere. This thing drops out in the non-included limits, and so included limits, and I'm totally blanking about why that is, but it does. let me take large nu. Right, so what I was trying to illustrate here, so this is now field theory, okay? Yeah. So the n goes to infinity limit of this model. There's 0 plus. So this is a 0 plus 1 model, and as n goes to infinity, here we have a 2 plus 1. Actually, gauge theory living on a sphere. And that actually reminds me of Zohar's comment. So the UN gauge symmetry here becomes local U1 and actually also diffuse and also area preserving diffuse. Yes.
Just a trivial point. I mean, in some sense, if you have just any harmonic oscillators, that becomes also continuum. This is more interesting because the matrix degrees of freedom are more interesting. If you discretize space.
But there's no. Okay. I mean, I don't know. So I think we can. I mean, there's no obvious locality here at all, right? I mean, these things have matrix multiplication.
Yeah, but what I'm saying is that just because we're not used to this matrix notation in some sense, I mean, it's just a little bit tricky that it comes out, but in the end, it's a discretized version.
I mean, I don't know. Look, there's nothing magical happening, right? But the locality.
Well, it's not
One
magic.
second. So it's because you have to get. I mean, you have to get this commutation relation, right? So it's not. So the map to this local theory only works because the matrices are strongly supported near these. This is a particular subset of the matrices, so that they this commutation. Very said differently. No, I think this is not true, but yeah. So a typical matrix here is not local, not naturally represented as a local field theory. It's fluctuations about this particular preferred set of matrices in the field theory. So I think it's not that obvious actually. Yeah.
What are these area preserving differences?
Yeah. So actually, by the way, this is even before string theory. The reason people got interested in, one reason people were interested in non-commutative field theories is precisely because they tended to you get this mix of internal and so space-time and internal symmetries from the UN actually. So getting the full diffeos never really works. But yeah, you do get this. It's a bit non-trivial. So this UN. I'll tell you how it works in a second. But the conceptual point is that it gives you both this internal symmetry, but it's also mixed with this space-time symmetry. So there's a whole approach to quantum gravity called non-commutative geometry, and their main point is this one. Okay, that you get area preserving diffeos out of UN. So how's it?
But that works with
Into the yeah. Actually, yes, you're right. Yes.
Quick question, what's this epsilon IJK?
Yeah, it comes out once you start doing these things. This one.
Yeah.
I think it's all. Okay.
Disappears from
I would not. It has not been dropped. So it's somehow things are being. Yeah. Okay. I can't remember exactly where it shows up. This whole thing is squared, right? And I think it makes it. This whole thing combines this. Yeah, maybe. Yeah, that's probably. Yeah. That's something. Yeah, they could. Yes.
Comment, if you were to take one of these other vacuoles that you didn't want to consider,
Yeah,
you would get some non-abelian symmetry.
Yeah, well, that's good. Yeah, maybe. Yeah, that's right. And then the field theory is might be that. Yes, sorry. Yes, is one. Yes. And right, so you could consider. So if you consider, so we have one sphere, that you could sort of put two spheres in the matrices, and then these are. You can get non-abelian gauge fields as well.
But do they actually emerge with the same coefficients? Because this is important for the emergence of current symmetry.
I think they must, because this is how you get these constant D-branes in string theory give you non-abelian gauge fields. Yeah. Let me. I wanted to mention this. So yeah. Let's see. So okay, it's going to be a little bit schematic, but.
Are there other ground states that you guys are subleading at large
Yeah, so it depends on, so in this bosonic model, this ground state is actually metastable in the quantum theory. It's not the true ground state. So, and indeed there are a whole bunch of other minima. So is that what you meant?
I was asking the computation is subleading at large.
Yeah, they're not talking. Yeah, expanding about some. Yes, that's right.
Is it obvious whether this Billion gauge theory is compact or non-compact?
It's a U1. Yeah.
It's a
And yeah, I mean, yeah, because it has to come from it comes from the UN, which is certainly compact.
okay.
And so to Max, to this point, so let me see. So let's see if we can actually do it. So U, right? So X goes to U X. Okay. Can everyone actually see? Maybe it's not. I'll just try a little bit here to finish. I might need this space. Okay, so now let's consider X. So then X classical plus A goes to U X classical plus A. U dagger. And now let's write U as e to the IT. E to the minus IT. Let's expand this, that's always easier to do that. So and then we're going to get X classical plus, very good, plus A, plus there's going to be something like an IT commutator A, commutator X classical. That's from one of these T's with this X. And by this map that I just told you, these are the generators. So X classical, remember, are these J's. And this whole thing is like a derivative of T. So this term is the U1. Right? So when we're commuting the X classical is like these J's, commutator of J's is So the way this first term is the U1, becomes the U1. But the next term is now something like I T with A. And this term, it turns out, is an area observing your field. So it's, well, let's see. So it's going to be, so A, it's little a, I goes to AI plus di phi plus, okay, this is not going to be right, but very schematically, it's dA with some sort of phi here, where this is such that, sorry to show it. There's a D, there's an A, there's a phi, and there's some contractions. And I mean, it's such a, right, it's something like that. I mean, I can look it up if you want, but I'll
Wait, it's not labeled by a vector field on the sphere though?
yeah, it is. There's some cross.
So it's like a zeta dot P.
There's like a, yeah, it's, that's right. So if you're on the sphere, right, and so there's some crosses and stuff in the right place. And so it's a different one along the sphere that preserves areas. Let's see. Can I do Yes, that's right. 2D and those doing analysis area. Right, it's the space diffuse. That's right. Yes. I can try to look up. I can look it up later. There's some. It's some. You do the Moyal map of this term, it is a transformation of the fields that keep you on the sphere, and what you would get if you did a coordinate change on the diffeo on the sphere. I don't remember the exact form.
So phi is like phi transforms.
Also, this phi is not.
It's not the other. Okay. Is phi a component of the graviton in some sense that you need to make this invariant under? Is that a way to think about it, or?
I don't know. I was just thinking about it as a scalar.
No, I guess I'm just kind of surprised that you write generally covariant, not fully, but almost generally covariant action without a metric. Is that
I think in 2D, it's
2D is too.
There's an area preserver, if it works as a variance.
But there's at least one propagating field here, the phi field, right?
It's the same thing. The VF version of the VF list is the same.
Can you somehow eliminate phi by putting vector strengths, maybe on the original matrices or something like that?
No, but phi is good. I mean, it's very reasonable as a phi. So there's a sphere. There were 3 matrices. There is a 3rd dimension, and the sphere can wobble. Okay, and it has a maximum field on it.
Sure, but let's say that you're interested in a theory without the phi, could you constrain the axis to be exactly on the sphere, no modeling? Would that result in a theory without
Well,
the
no.
phi?
So okay. So these, for example, the models with just 2 matrices, where you get a sort of non-Euclid plane, those don't have a transverse. So you can certainly get you can certainly get a 2D theory without a like this. I think in this kind of setting it's quite natural. They don't have that, but you could get you can't. There are models without scalar fields.
So Sean, would it make us take a 5-minute break at some point?
Like one more thing, and then that's just what I was thinking. Yes, I'm indeed definitely. We're 1/10 of the way through. Okay. Yeah. A break's coming. So okay. So actually, this was not mainly what I wanted to talk about, but this was the. So given this, this is so matrices are definitely a path to quantum field theory. Okay, you can, and this is how D-branes work. This is how the string theories happens all the time. Okay, but one would like to understand, like what really happened. I mean, how now I'm going to take a step back to the matrices and try to understand how the entanglement, or how from the sort of more microscopic point of view do you see this locality emerge, right? Because say someone gives you some matrix wave function, but it doesn't, for BFSS, it's probably not so. It's not going to be so simple. There's some classical configuration that you expand around to give you even in this model, when nu is not big, it's just some quantum state. Okay, and so one would like some more microscopic diagnostics for the emergent locality that don't just involve solving the model, because obviously most of the time we're not going to be able to solve it. Right. So what I'll talk about in the remainder is a sort of starting to think about the entanglement in matrix wave functions that underpin this kind of emergent locality. Okay, but this is sort of a motivation for doing that. Right? Yeah. So.
Here, we reconvene in 5 minutes, 11:15. So does phi transform weirdly under your area preserving diff, or does it transform like a normal scalar field on the sphere?
We could look it up.
Okay. Sorry, I don't mean to.
Actually,
I'm not sure I agree with.
probably like a. I think it is like a normal scale.
Like a normal scalar. Okay.
Then F just transforms.
Okay.
How's it different? Where are the derivatives on the diffeo? They're on the thing that acts, right?
They're on.
Yeah.
It's both, right?
It's like
weird.
dx prime that multiplies. Oh no,
Well, I think there's both, right? It's like zeta. Pardon me. There's like zeta dA and also
what are
A.
these curly L derivatives called? Yeah.
Lee derivatives.
Yeah, something like that.
So there's I feel like there's both actually. Although if it's area preserved, maybe some of them are 0. I don't really know, but I'm not sure I agree with what Zohar said, because there's at least one extra scalar field. I always thought 2D Maxwell can be written area preservingly.
I was just trying to give
Okay.
while I was on the stage. I'm not sure.
Right, because 2D Maxwell is invariant area preserving, but it has nothing going on. That's sort of why I thought why that's possible. It has no local degrees of freedom.
I see, but is phi the same as a Maxwell field in
It's not
in 2D?
Yeah, it's not 2D. Yeah. There's also the ties.
Yeah. No, but they're 2D's area preserving diffs fields.
Yeah.
So
these are 2D
ones.
area
So kinematically it makes sense to ask the same question, but I think that I don't see how you could write that action in a way, the grad phi squared, in an obvious way to be invariant under any sort of diffs, right? It's like G upper mu nu, d mu phi, right? And that just seems to not, right? There's something magic. I feel like something magical must be happening.
Okay, it's good. Actually, to be honest, I have not sat down. Because it's sort of easier here. I think so. This is the same as this, right? Just this is sort of unpackaged into to make it a bit more.
Right. Yeah.
And maybe here it's easier.
So I don't mean to interrupt you. You might want to get a coffee or something.
Yeah, maybe I will.
Yeah. But there are no examples with people constructed like so with UN, this map is reducing between area preserving
Sorry, you need to go this way. That's a fire exit. You need to go back through the lecture theatre. Thank you.
Hello. Hello.
I go? Yep, you're right. So maybe let me recap before I go, because this was an important. So with matrices, yeah, to contextualize what I was just saying. So one matrix, you get a 1 + 1 scalar field with this sort of max BFSS theory. Maybe you get well, M theory, right? You get gravity, Susie, presumably. The one I talked about with sort of this model with 3 matrices, I got a Maxwell theory. I do want to mention, because given the audience, there's a nice model with 2 matrices that I mentioned in passing, where you do get Chern-Simons, including on the Billian Chern-Simons. And I think it's pretty cool, and it should be better appreciated, and you should read the oeuvre of Tong, Turner, and Dory. Have a whole sequence of papers on this model. And it's really okay, so quantum Hall effect, a lot of electrons, disorder, Coulomb interactions is horrible, right? But then you get this beautiful Chern-Simons theory out, and you could ask, what is the minimal microscopic theory that is sort of discrete in some sense? What's the minimal microscopic theory that preserves as many of the symmetries of Chern-Simons theory that you have? Okay, and that's this matrix model. It has this huge UN symmetry. That's I think this is the nicest discretization of Chern-Simons theory, and I'm not going to talk about it. You should read it. Yes.
What is the philosophical place of Morel symmetry?
Yeah, I don't. I think that is.
Your model is not Morel invariant, even though you call it Maxwell, I would say it's not.
You want gauge field? Is you happy with that?
Kind of non-relativity.
How about lattice gauge theory or something?
I don't know. Non-relativity theory.
Yeah. So I absolutely. You know what? I totally. In fact, yeah. Well, do you understand how it works here? No, but it's very, very confusing. I thought it's a deep question where Lorentz invariance comes, and it's very confusing that in our universe there really is no violation of Lorentz invariance, and that kind of should be. it's a bit. Lorentz invariance is a very, very good symmetry. If it's emergent, it's really non-trivially emergence. Yeah. Okay. Let me just leave it. Okay. So suppose someone gives you a matrix. Right. So for lattices, we understand if you have a local lattice model, the entanglement is really constrained. The area laws, the Lee-Robinson bounds. There's all this stuff you can do from the locality of the Hamiltonian. Matrix Hamiltonians also have a structure. They have this UN symmetry. Okay, what does that mean for the wave functions that you get out of matrices, and how does the locality of these emergent theories manifest itself in the matrix wave function? I think we just need to understand this question, and I think we know the answer in these simple cases, which is not enough, but it's a starting point. Okay, so where is locality? What's the easiest way to see the locality in the matrix wave function? In the states. So what I'm going to talk about is based on a proposal by Daz, Trivedi, Gauss, Mendel, and Kaushal. And it goes like this. So if I've got a region of, the nice thing about these matrix theories is that the space is somewhat there to begin with. There are 3 matrices, and each matrix is going to correspond to the direction of space. Okay, so you have some sense of how things are going to go. Okay. So suppose I have a region of space. So including normal field theory, and then I could define some function of the coordinates greater than 0 that defines the inside of this space, this region, for example, right? So, for example, f would just be x1, that would be half the plane. F could be x1 squared plus x2 squared minus some constant. That'll be a circle and so on, right? Given I have a function defines a region. So what I think the essential point that these guys made is that to define a region, you only need one. There's one inequality. There's one function of all the coordinates. There are many coordinates, but one function defines a region. Okay. With multiple matrices, you cannot diagonalize all the matrices, but you can diagonalize one matrix. You have enough gauge freedom to diagonalize one matrix. And so the natural matrix to diagonalize is the one that defines your region. Okay, so I'm trying to find a subregion. Right? To define locality is to find a subregion. So they say that what you should do by everything's going to be gauge invariant. Okay, so what it means is that it's interesting to look at so any matrix, right? x1 times x2 squared. Any matrix you want has eigenvalues, right? You can talk about the expectation values of the eigenvalues of any matrix you want, but they don't commute, so those are correlated, right? The idea is for any region, you should take you should do the following, right? So the description is, you think you've got a region, we want to find a certain region in the matrix theory. They say take this defining function and replace all these x's with matrices. Okay, so define a matrix. So let's say we're doing this case. To define the matrix, take f to be x1. Matrix now. These are coordinates. Now, as many of you are probably about to tell me, there is an ordering ambiguity when you do this, right? So, for example, x1, x2 squared is some region, x2 squared x1 is the same region, but in matrices these are not equal because x1 and x2 don't commute. Okay, so there is an ordering ambiguity. However, about these semi-classical saddles, the hope is that's not too important, and so I'm just going to define a matrix function, whatever you want. Could be x1, could be something else. Then the idea is you define a projection that is theta function, Heaviside theta function. Sorry, I'll get this right. Yeah, of this f. So, what does this mean? This is a fancy way of saying that build a matrix. So take f and diagonalize it. So in some basis, f has this form. Given this theta, then I order the eigenvalues, and I take all the eigenvalues that are less than 0, and I make a matrix that's ones, where this is an m by m matrix, where the mth eigenvalue is the last positive one. Does that make sense? So given a region, for example, I can define the index function of a region, right? You can take theta of f of x, right? And say if f is x1, right? Then this is a function that's 1 here and 0 there, right? It's the index function for any region you want. I can promote this function, this x1, to be a matrix, and I get this projection matrix. And this is a matrix that, in the basis, where you diagonalize this function, has ones and then zeros everywhere else. Does that make sense? So what it's saying is that this region should be associated to a subspace of the space of matrices where that's spanned by the positive eigenvectors of the corresponding matrix.
So to project to the region, you project with h.
I'm sorry, say again?
To project to the region, you project with h. Is that correct?
With what?
Sorry, that's supposed to be a theta, sorry. Not h.
So almost the same. Yeah. Theta. So this is a projection, right? Exactly. This matrix squared to itself, right? So that's right. That's right. So the analog of this index function that is 1 and 0 in a given region, every index function is associated to a projection matrix that projects you onto a subspace, what this subspace is that you take the matrix corresponding to your region and you diagonalize it, you order the eigenvalues, and the lowest m eigenvalues, you keep that subspace. Yeah.
So you have to some sort of map between your kind of emergent space and your matrices, otherwise you don't know.
That's right. This is a conjecture. This is a guess, and now we're going to see that what it can do for you. So what this is based on is, remember the case of a single matrix. You diagonalize the single matrix, and you've got these n particles with the eigenvalues, and there the eigenvalues did in fact build the space, and so restricting to the space of the lowest m eigenvalues was in fact cutting the space. Now, with multiple matrices, you don't have enough freedom. You can't diagonalize them all, but you can diagonalize one. So what you should think is, so basically, if you like, the eigenvalues are like the foliation of the space, or it doesn't have to be circle. So given some region, the eigenvalues are roughly, the idea is that each of these projections sort of corresponds to these, it's sort of like a foliation. So in 1D, with one matrix, you can partition the eigenvalues as a line that you can split up. Now you have a high dimensional space, but you diagonalize one function of the high dimensional space, and this gives you these sort of level sets of this function. But indeed, it's not obvious, so we're going to do a calculation and see what happens. And so what I'm going to do, in the ground state wave function, this quantum mechanics I wrote before, I'm going to calculate the entanglement of the degrees of freedom that live here with the degrees of freedom that live elsewhere. And it's going to give an area law, like a boundary law. Okay? So that's what's going to happen. Right, so yeah, so this paper was a bit, I mean, I think what I've said is all you need to know about that paper. Okay, it's a suggestion, right, about that it's simple, that I think it's non-trivial that you have enough information to diagonalize one function of the coordinates, and that's naturally associated to a region. That's the idea, and so I want to see if it works. Okay. So a region is you have to give me a matrix, right? And you diagonalize, and then we're going to work with the basis when this matrix is diagonalized. I don't have to work in, of course, it's basis independent, but that's the easiest way to think about it. So all the matrices, xi's, now get block decomposed. This is where the non-triviality comes in. Right? So any of the x's has, I think of it like a region in the region, some x's in the region, some x's outside the region, and then the off-diagonal guys. And those are the confusing ones. Right? There's some degrees of freedom that I want to think about. These degrees of freedom as being in this region, these ones as being outside, and then these ones are in both. Of course, we have a good precedent for something that's in both regions. It's called a Wilson line. Okay, so these ones, these degrees of freedom we're going to see are like Wilson lines that stretch across the boundary of two functions. And the entanglement is going to be very similar to the entanglement in gauge theories, where there are edge modes and so on associated with these off-diagonal lines. But to start with, right? So you want. I'll say it one more time because I somehow get the impression it is very simple. Okay, so a region is defined by a function. I upgrade that to a matrix function. I can diagonalize that, and that is going to give me a notion, a preferred basis. But because there's more than one matrix, all matrices are not diagonal in that basis. Most matrices will be off diagonal in that basis. There's a privileged matrix to define the region. So given this basis, I now need to make sense. Now the idea is that these guys are in the region, these guys are outside, and one needs to make sense of these off-diagonal guys, because these are the non-perpetuity of the matrices.
In some sense, which of the matrices you choose to diagonalize is up to you, and you can get
in different regions.
outcomes.
Yeah, it corresponds to different regions.
But in some sense, the physics would be equivalent because you're talking about the same matrix in the first place. I mean, matrix.
Physics would be equivalent. I mean, it's just the way. So if it's different choices. So I'm going to literally trace out. These are harmonic entries, like harmonic oscillator in open space at each point with this gauge constraint. I'm just going to trace out a bunch of oscillators and ask how they're entangled with the oscillators.
But there shouldn't somehow be a reason to prefer to diagonalize one matrix over the other.
there is
make
not.
a choice.
So there is it's a choice.
Should not be, you make a choice.
That's right. And that
So
choice.
the other choices that you can be bounded.
Well, there are different regions. And that's the idea. So you've got a sphere. Well, let me say you have a plane just to make it a bit easier. I can take this region, or this region, or whatever I want. Okay? And partitioning this Hilbert space. So I'm picking some oscillators and some other oscillators and putting them in different boxes. A different region corresponds to a different partition. Diagonalizing. You don't have to diagonalize the matrix, right? The only reason to diagonalize the matrix is that I want to pick out some subspace of oscillators, and I do that by picking a subspace of the matrices, and that's what the region is, a choice of different subspaces. Sorry? Well, of course, there's a U. Yeah, right. So I believe that yeah, that's fine.
But I think they define the same projector, though, those different functions, no?
Not defined. No, I think they won't, but the differences will be small in some sense. Okay. Let me show you how it works, and then we'll see that none of this is too scary. It's quite simple. So if I want to think, so I'm going to want to trace out some matrices, some components of matrices, and be left with these. And I want to calculate entanglement. So it turns out that the dominant contribution to the entanglement comes from the Gauss law, which is particularly robust. Okay. So now the Gauss law also decomposes, right? There's a G, right? And G, of course, also decomposes into 4 blocks. However, this block also acts on these off-diagonal guys. It makes sense because these have half a leg in one leg on these coordinates. So let's write it out. So G sigma sigma. So remember G was pi x pi. Okay. So if we write this out, it's going to be x sigma sigma pi sigma sigma bit. But there's also going to be an x sigma sigma bar pi sigma bar sigma minus x times pi so because there's an internal index, right? So one of the indices is fixed, so live in this region. But of course, when you multiply, right, this is x pi minus pi x, the index that you're summing over could also run over all the regions, right? And so this component of the Gauss law is that this whole thing has to equal 0. And so let's write that. Let's call this bit G hat sigma sigma, and I'm going to call that bit Q. And so the Gauss law, this component of it now becomes G hat sigma sigma in the state just Q. And so how do you think of this? You have some region, and there's sort of some Wilson lines coming in that the charge, right? The charge is balanced outside. So these off-diagonal modes are charged under the under the U1, sorry, the UM, let's call this M. There's a UM that's only generated by these degrees of freedom. That's this bit. But these off-diagonal guys are charged under it, obviously, right? They transfer. You rotate, there's a UM, the UN minus M, and these are charged under both. Right? And so they're here on the right-hand side. Said differently, there's a global Gauss law. The total charge has to vanish, but inside a region there can be a net charge, right, which has to be cancelled by the charge outside. That creates an entanglement between the outside and inside the outside. So that's the entanglement we're going to calculate in this one. Yeah, so yeah, all right. So how am I doing? What time is it?
You have, let's say, 25 more minutes.
Okay. Is that minus epsilon or plus epsilon? Okay. So suppose now I take this state. This is the ground state. the same ground state we were talking about earlier, and I trace out, so I can build a density matrix of the ground state. Right? And now I'm going to trace out all the oscillators that are not in that region. Okay, and I'm going to call this the reduced density matrix of that region. We can check.
Yeah, we're going to do this for all the matrices.
Yes, that's right. That's right. These are yes, I think that's right. These are all. I'm tracing out all the matrices, all the components in the other matrices. In turn, we can easily convince ourselves that this reduced density matrix actually commutes with this SU. This is an SUM. How does that go? It's pretty simple. So G only acts, the G hat only acts on these signals that are not getting traced out. So I can just move it inside the trace. I'll say it in words perhaps. So I can move this G times rho. The G can just go through the trace because it doesn't act on these signals. So on this state, G has to be equal to Q. Okay. But Q only involves these degrees of freedom. Right? Because Q is built out of these off-diagonal oscillators. And so with the Q, you can cyclically permute the trace and you get zero. It's trivially true. And so this is a weird equation, right? This is a state, but this operator only acts on one set of oscillators, and this operator only acts on another set of oscillators. Okay, that's why it works. But what this means is that right. So this is a generator of a symmetry. This is a matrix. This means these have to be identities on the representation. These have to be a Casimir on the representation. So this implies this density matrix is a sum over representations of UM, the states of UM, with some probability normalized by the dimension of the representation, and it has to be the identity. Okay? Because it commutes, right? These are all the generators. If I have a matrix that commutes with all the generators, it has to be the identity on each representation. Okay? And so this density matrix, the only information in the density matrix is how much of each representation there is. Okay, and so PR is the probability of finding a given representation. This is the dimension of the representation just to normalize. Right? So this is quite a big simplification. So the entanglement has to do with so the whole thing is a UN singlet. I've taken a subset of the degrees of freedom, right? And I ask, what is the UM charge of this subset of degrees of freedom? And the entanglement is, okay, so the entanglement of this density matrix, just plug in this is, you're going to get the sum of our representations, PR log dot dr minus PR log dr. This formula maybe familiar. Right, so there's one bit that's just the dimension of the representation and the probability of finding it, and then this is the entropy of the different representations. So what's going to happen, it turns out, about this classical fuzzy sphere, is that there's a larger limit, there's one representation that dominates, okay? So all of the PRs are 0 except one, which is 1. And so what will happen at large n is that a single R dominates. And so the entropy then is just the log of the dimension of that representation. Okay? I'm going to calculate that and what this is going to be, right? So I'm going to take the fuzzy sphere. I'm going to define the region F, okay, is going to be the x3 direction. So these cuts correspond to cutting across the sphere like this. And we're going to find that this logarithm is precisely this this perimeter here. It looks like sin theta across the sphere. And I think it's true, in fact, for any cuts. Right? So this, the dimension, so this region has some transformed under un, and the dimension of its representation knows about this area, which is the geometric quantity. So that's some evidence that this cutting thing that we did is not crazy. So you can, in other words, you can see the emergent geometry in the gauge theoretic entanglement.
It doesn't see what kind of fields propagate.
No.
It just sees the existence.
And there is a subtlety with UV dynamics, but yes, the take-home message, as the coffee starts to wear off, is that this gauge theory is very robust. It's a very, and the reason the one representation dominates ends up being closely related. Well, okay, we'll see in a second where it comes from. It's a very simple fact about these matrices.
So
Yes.
for you to explain what kind of form of the beams. So the case of the volume law, how does the entanglement?
It's not a volume, right? It's an area law.
Yeah, right.
A perimeter law.
Yeah, but for comparison, I want to see how.
Oh, well, yeah. I'm not sure. For example,
Yeah.
this call this angle theta. All right. So the area of a boundary law, the entanglement goes like sin theta. For a volume law, it goes like sin theta squared.
I see.
It's a different function. It's a different functional dependence on theta. Yes, so it's not quite as beautiful as it should have. So yeah, of course. Yes, it's. I'm sorry. Obviously, that's right. There'll be a prefactor. We'll come to the cutoff. Unfortunately, it's not as nice as it should have been as a cutoff.
So to get back to Max's point, it says on the proviso that you choose one of these vectors. If you chose the size of this.
Yeah, everything I'm doing. We're going to see that the state is super supported close to this factor, right? I mean, plus, that's right. Yes, it's one of the right.
So you thought they were going to generate, so you did chose any of them.
Yeah, it's a semi-classical. It's the entanglement. Yeah, I'm working on it.
I'm just raising it now because the fact that you get the perimeter is of course because the radius of the sphere has to have the right relation to the radius of the sphere. And if you could have chosen the sphere, that was much
No, it's not trivial. So I think there is an issue with this multiple vacuum in this model, but I think it's fundamentally red herring. The additional symmetric models is all going to be fine. Okay, but it's a fair point, but I don't think it's at the heart of it.
But in risk calculation,
It's not trivial that this is a particular functional dependence on theta. It's not fixed by symmetries, as we'll see.
and you are not expanding around any vacuum. This is just solid matrix.
Well, I'm going to write. There's going to be a state in a minute that I'm going to write down, and that state is going to be strongly supported on this classical vacuum. Yes. And we'll see in a second. I mean, I'm not going to make up the state, but
But whether you do this like so far, it's independent.
everything so far. Yes, that's right. Exactly. Up to here, everything is just general. That's correct. Yes, yes, that's right. So in particular, if you knew the wave function of BFSS or some more complicated model, this is something you could calculate.
Can you do this with Susie as well? Interesting.
We have not done it in the Susie case, but semi-classically, it's the same in the Susie. I don't think it. Actually, let me not lie. I'm not sure. I haven't thought of it. And actually, the ingredients are all in place to do the Susie case because in this previous paper with Gigi, we did do the supersymmetric case. But I I need a new student of the college, it's pretty precise. All right. Yeah. So let me just sketch how this goes, at least. But yeah, this is an important point. This is a general quantity that's universally defined given the matrix quantum mechanism with the UN Gauss law, right? It's a natural thing, and there will be these sectors, and it's a very generic fact of these non-commutative theories that it ends up just being one representation, and this representation knows about the area. Okay, it's a kind of quite a universal thing, and I'll try to see that. Very good. So in essence, it is, so we're going to partition, as I said, in X3, right, along these ones. So we've already got this guy diagonalized, right? So we're going to keep, the subspace is going to be this. And so now look what happens if you take the other matrices that are not diagonal on this basis and you partition them. The off-diagonal guy is low rank, right? And that is crucial. Okay, so it turns out, and it's very generic actually, that in when you have these matrices that generate non-commutative spaces, the off-diagonal, and you diagonalize one, the off-diagonal ones are low rank. Okay, and that is what makes everything tick. And not only that, what is this n? So n, right? Let's take this to be the nth element, or the nth plus one in this matter. Right? This is like m. Yeah. If we take the sphere, we cut it here. It turns out that this quantity is sine theta. So this is theta. I guess this one is cosine theta. You fix this direction, right? This is z. You will like L is n minus this. Okay. This one is n over 2. This one here is n over 2 minus m. Okay, so this is, you do some trigonometry, this angle turns out to be exactly this. And so this off-diagonal matrix already has the geometric information in it. Okay? And the way we're just going to sort of shunt this through, it turns out that this thing is going to control this dimension. Okay? Now, this fact, so maybe before I do it, so there's a few calculations to show that basically this ends up being the entanglement. Okay? And roughly, the way it's going to work is there's going to be a, let me just do it. Yeah, given that I don't want to, so in essence, what let's see. So we're trying to understand, we've got this G, which is a matrix, and we're trying to understand what representation of UM this transforms the state in, right? Under what representation is, if UM is the state, find itself. So remember, G was equal to this Q, which was written in terms of the off-diagonal, so it was G equals this thing. Yeah. So the charge, the G was equal to the charge, and the charge was given by its off-diagonal modes. Okay, what is, now I need to tell what the wave function is indeed. So remember we wrote x. Now I just write x as classical plus delta x. The wave function, well, this thing was this fuzzy sphere. So the wave function turns out to be, I can expand this in terms of modes. So I'm going to write delta x as a sum over some coefficients times some basis functions, which are closely related to the spherical harmonics. Okay, they're not quite, because they have an extra I index. There are 3 matrices, and so there's some vector that goes in there, but they're basically spherical harmonics. And the wave function of this ground state It's simple, right? I take this, I plug this into the potential. Remember there was a quantum mechanics of the potential. It was a total square. You expand it about the minimum, you get some quadratic action for the fluctuations, and the wave function is just the Gaussian in those fluctuations, right? And so psi of x is just e to the minus sum of all these modes, matrix modes, some frequencies, and this, and these frequencies turn out to be very simple, right? So I've expressed, so the wave function make a large unit as a unit here, in fact, 2.5. Okay, so there was this fuzzy sphere, and now the wave function is some Gaussian fluctuations localized on this fuzzy sphere. Okay, that's what this is. But to evaluate this, so that's the wave function. On this wave function, these x's, I can just replace them with x classicals. But pi is 0 classically, so you do need the fluctuations to calculate the pi's. Okay. Nice. So, but these are these very low rank matrices here. Right? Okay, and so that simplifies this thing a lot. And so this basically becomes, and these guys, I just have this sine theta in it, so I'm just going to write them as sine. So I said sine theta, obviously it's like m squared sine theta. So this thing has some m squared sine theta in it, and some over Lm, pi Lm. I can also decompose pi in the same basis. Right, so these terms become this pi, and then there's a matrix. There's some matrix left that comes from multiplying these modes with x classical. The x classical was a low, only had one non-zero entry, and so what you get is a matrix here that's only non-zero along 2 lines. So basically, just phi m dot this line. Alright, what am I trying to, so here there are m squared momenta, right? Because there are a bunch of order m squared generators. But when you multiply them with this classical bit of x, almost all of them get killed, except that, and you end up with this very low rank guy. Yeah, maybe this is too much detail. Let me. So what you can see easily, this is a very low rank representation. Because most of these pi's don't contribute. Okay, so in fact, it schematically has the form of a vector psi pi So these are sort of vectors, some vectors, and so this is how UM would act on a particle that's moving on CPM. Right? So say you got CPM, that's like a sphere, right? A particle moving on a sphere has a natural action of UM, and this would be, and the Hamiltonian would be trace G hat squared in that case. Okay, so the way UM acts is like a particle moving on a CPM, where the volume of CPM is this sine theta. You count the Hilbert space of that particle, and the log of that ends up just being the sine theta factor, basically, right? So this, yeah. Let me, when I say these words, so this is like a particle on. So it acts the way the UM acts as it would act on a particle moving on CPM. Because there's only, it's like a vector, it's not a matrix anymore, it's just a vector. but this vector is constrained to have a magnitude, right? These are just rotations, right? And the magnitude is fixed. This is like the size. And so then you can easily calculate trace g squared. And so these representations are just classified by trace g squared. They're very simple representations. I'm sorry?
Is the particle in 1 plus 1? He's asking.
Particle in, no, would it be 1 plus 1? Edge modes. Maybe, no, let me, let's talk later. Yes, maybe let me think about it. So all this is I'm just making a representation theoretic statement that will allow me to calculate that right, because I want the dimension of the representation. Okay, so first I found it's a relatively simple representation, and a particle on CPM, its states are just polynomials on CPM, and you can just and once you fix the Laplacian, you know how many polynomials there are with a given order, right? And so you count those. That's some binomial, okay? And you put you put this binomial into this. The binomial is like e to the something, okay? And the number of states comes out to be this, something like this. Does that make a bit of sense at least? So I'm trying to count the dimension of the representation. The representation is quite a simple representation, and I'm saying I can't count it. All right. There's one subtlety into the last thing I say. It doesn't quite work like that. And the problem is that when you're counting, this is an interesting physical point, not a mathematical one, so I think it's understandable, even if the last 10 minutes didn't come out understandable, right? And the problem is the following, that here's your sphere, here's this region, this is M, sort of this size, and you're sort of counting the number of modes in this region, but the modes can be very high frequency, and there's a cutoff, right, N, there's a cutoff on the theory, okay? However, the underlying coordinates don't commute, so suppose x, just for simplicity imagine x and y don't commute. Then there's an uncertainty relation, delta x, delta y, has to be bigger than 1. Okay. So now there's a sort of angular version of that. Let's call this angle phi, this angle theta, right? If delta phi, the whole range that you have is just m, right? So delta phi is an example. Then delta phi has to be bigger than 1 over m. Okay? So the fact that you only have a certain amount of space here means you can't resolve shorter distances than 1 over m along here. So does that make sense? They don't commute. The coordinates, let's take this coordinate and this coordinate don't commute. So if you only have that much space, you can't resolve something smaller than 1 over m here. Okay? That means that the cutoff in these entanglement calculations ends up depending on this size m. And this is called UV-IR mixing, and it was showed up a lot in the early 2000s when people did non-UV filter. Right? You want the shortest distance you can see here depends on how big the space is that you're considering, and that screws up what I was saying. So, one second, just 1 second. So, what in particular what that means is that this sine theta does show up, but there's another theta dependence from some effective cutoff in the matrices. Okay. So you can get rid of this if you change the question. Okay, sorry, to write down what happened. What this means is that in addition to the sine theta, that sort of sets the radius of the CPM. An m is in 1-to-1 corresponding to theta, right? Theta is the angle. there's an extra theta dependence from this effective cutoff. And where it shows up is in the various sums. When when you calculate, there's some certain sums of a spherical harmonics that show up, and you get a sum when L goes from 1 to n. That's fine. But M, which is like this guy, it goes from 0 to not to L, but to the minimum of L and M, which is exactly this 1 over M cutoff I'm telling you about. Right? There's a sum that in the period wants to go. You would have thought it should go all the way to L. I've got this like mod M, but actually it gets cut off sooner, and this just comes out of these matrices. But the physical reason is this kind of uncertainty in space. Okay. So, and this then introduces some theta dependence. So basically, there's like a spherical harmonic of theta squared, and if this went all the way to L, y Lm theta squared sum over m up to L. This is something that doesn't depend on it's like 2L plus 1 or something. It doesn't. The theta dependence drops out. If you cut it off too soon, you do get some theta dependence, and it messes up the area. Okay. So if you want to get the area law, what do we do? In quantum mechanics, when x and p don't commute, we have to build some kind of wave packet. Right? You have to do something with x and p at the same time. Right? So what you can do, which will be the last thing I say, is you can ask, what is the variant? So this quantity is basically the charge in the subregion, like the SU charge in the subregion. That was for the covering. It could also be carried by modes. Angular momentum L less than some point. Okay, so we have to smoothen the angle. So if you, basically this was too sharp, the question was too sharp, and so you shouldn't ask about arbitrarily all the charge, but only the charge is carried by suitably long wavelength modes. And if you do that, then these both get cut off with lambda. Well, this gets cut off with lambda, this gets cut off with L, and as long as lambda is less than M, theta dependence drops out. Okay, so you need a kind of smooth, sort of coarse-grained. So to get the area law, you need a slightly coarse-grained. Right. So there's no relativity. This connects to what I said at the beginning. There was this star product, right? Then it goes over to a dot product, and then goes to infinity. So if you are working at finite n, you've just got to be a bit careful not to look at too short distances. Otherwise, you're going to get so sort of order of limits. But it's a little bit unsatisfactory because entanglement then goes like this cutoff that you sort of put in by hand. And the whole nice thing about these matrices is they should come with a cutoff. N should be the cutoff, and it's not quite how it works. Right, I think I've talked too long. Thanks for listening.
So, in view of time, we need to take one or two more questions. If they're urgent.
Sorry. Should have told me. Okay.
Okay, in that case, let's adjourn for now. So this is the end of today's session, actually. So we'll have lunch at the business school as usual, and afternoon is free.